Okay, so this is LeetCode 572, subtree of another tree. So given the roots of two binary trees, root and subroot, return true if there's a subtree of root with the same structure and node values of subroot and false otherwise. A subtree of a binary tree is a tree that consists of of a node in a tree and all the node's descendants. The tree could also be considered a subtree of itself. Okay. So let's look at an example to see what they're actually talking about. So here's example one. We're given this tree called root, which is pointed to this node right here where I'm hovering 3. And then we're given this subroot tree, which is called, which is pointed towards this to this node here, this 4 node. And basically what we're asked to say is return true or false of whether or not this entire tree, let me scroll down a little bit, whether this entire tree is a subtree of this tree. As you can see here, this tree here is circled here, so it is a subtree, so that's why we're returning true. This example, we would return false. It looks like it's a subtree, right? It looks like it's kind of the same thing, except for this subtree here has an extra node, this 0, that isn't in our subroot tree. So we would return false. So it's not the same structure, and it's not the same structure or values as this subroot tree. So we'd return false. Yeah, so if you're familiar with this same tree problem over here, this is kind of a continuation of this problem. It's basically built up on that other problem. So this same tree problem, which I covered in another video, basically we're given 2 trees and we want to return true or false whether they're the same tree structurally and the same values, right? So you can see that this problem that we're looking at now, 572, is just basically same tree but with a little bit added more complexity, right? It just means that this same tree can be nested somewhere deeper in this root tree. So as a hint, basically what we're going to do is we're going to use the same logic that we've had in this solution as a helper function, and then we're just going to do some recursive calls. We're going to write our function so that it basically, so root at this point is at this node, right? What we're going to do is we're going to call, is this root, or is this node right here, is it the same tree? We're going to use the helper function same tree. Is it the same tree as this tree? If it's not, then we can just pass root, or we could recursively call our same function, our subtree function, right here with the left and the right children. And then we'll just continuously keep going. So we can just go ahead and copy that code and just paste it over here. Yeah, and then I don't think we need all this type information, so I'm just going to delete it. Okay, so this is our helper function, right? And because it's not the, because I've covered this in a different video, I'm not going to fully explain it. Maybe I'll go over it briefly at the end, but this is what our helper function is going to do. But what we're going to do for this function is subtree. What we're going to do is we have basically 3 distinct cases, I believe. Okay, so I brought this into a whiteboarding tool, and I'm basically just going to try to explain the 3 distinct cases for our recursive function. So we need some base cases, right? So what are going to be our base cases, and then what's going to be our recursive case? So let's go back into the whiteboard. So one of our base cases is going to be in the instance where root is a full tree and in the instance where subroot is equal to none, right? What do we do in this instance? Well, is subroot a subtree of root? In this instance, it actually is. Why is that the case? It's because if a node doesn't have a child, then its default value is going to be equal to none. And we know that by, give me 1 second, I have to sneeze. Okay, sorry about that. We know that by the tree node class definition that they give at the top of LeetCode, and I just have a screenshot of it. Right here basically means if they don't pass a left and a right value or left and a right child value, then it's going to be defaulted to none right here. Okay. So we can see that none is a subtree of this tree, big tree, because none is equal to none is found in all of these spots, right? So technically this is a subtree, this instance. Okay, what about case 2? What about if root is equal to none and subroot is equal to something, a big tree? Would subroot, the tree on the right, be a subtree of this tree on the left? This would be no, because, well, you could see it's just this whole tree over here. There's nothing over here that on this tree that could make up this tree, if that makes sense. So this instance would be no. Okay, so case 3. What about in the instance where we have our root trees populated, and I don't have values in here just because I don't think it matters for this instance, but it's just this concept is what I'm trying to get across. So our root tree is populated and our subroot is populated. Is subroot a subtree of root? There's a possibility, but we have to do recursive calls on our root value. So we would have to check, basically what I'm meaning is that we'd have to check at this point, when subroot and root are equal to these values, we would check, okay, we would call our helper function same tree, which we've copied the code, right? We've copied it here. We're just going to call our helper function, and we're going to say, is this the same tree? If it's not, then what we're going to do is we're just going to pass root, or we're going to do a recursive call, and we're just going to say, is subtree with root dot left, which is this child, this subtree right here. So then we're going to do the entire calculation. We're going to say, is this subtree the same tree as this tree right here? If it is, then good, then we can return true. If not, then we would just move downwards again, right? And then it's also good to remember that we're going to also do a recursive call with the right subtree. So at this point, if root, say that this was like a 4 here, and then say that this was an 8. Okay, at this point, when we're both starting at this topmost node, we're saying, are these the same values? Obviously 4 and 8 aren't the same values, right? So what we're going to do, like I said, we're going to recursively call our is subtree function with our left child, or our left subtree of this root, and our right subtree of this root. So then we're just going to do it on both sides. We're going to say, is this subtree the same tree as that? Is this subtree the same tree as that? And then it's possible that maybe this subtree would be the same as that, and then our helper function would catch that. I hope this explained the recursion a little better, but I'm going to go ahead and get into the actual code. Okay, so getting into the code, basically what I'm going to try to do is just transfer these test cases, or these base cases, over to the code. So the first scenario that we're going to add is this case 1. So if subroot is equal to none, then we can just return true, because we know that that is going to be a subtree of this root here, because we know that there's default values of none and none. Okay, so if subroot is equal to none, then what we can do is just return true, right? Okay. What about the other case that we had? What about case 2? If root is equal to none, in that instance we would return false because subroot can't be a subtree of this if it's equal to none. If root is equal to none, and what does this also imply? If we get to line 11, this also implies that subroot does not equal none. So this implies that subroot equals none. We don't really need to add it in the if statement, but it's good to know because that's kind of the logic of here. It means that if subroot or if root is equal to none and subroot is not equal to none, or it's initialized to something, then this is going to be this case. And then what we're going to do is we're going to return false, right? Because that's what we talked about in this example or in this test case. Okay, and case 3 is where it gets interesting. This is going to be the actual this is the actual recursive case part. Basically, before we actually do the recursion, we're going to say we're going to call it a helper function. So we're going to say if self dot is same tree with root, and then subroot. If this equals to true, then we can just return true, right? So this is the part where we're calling our helper function with our current values of root and subroot. Okay, and then otherwise, what we're going to do is we're just going to call root. We're going to do recursive calls of root and subtree. So we're going to do self dot is subtree with what is it? Root dot left and subroot. We're not going to change root. We're not going to change subroot at all. We're only just changing whatever this root value is going to be in a recursion. And we're going to do self dot is subtree. I think my laptop's dying. I think we'll have a little bit of time though to finish this. Self dot is subtree with root dot right and then subroot. Right? So as I was explaining here in this case, if this doesn't come out to being true, if this comes out to being false, then what we have to do is we're going to recursively call is subtree with the subtrees, or the left and the right children of root. Right here, what these arrows are pointing towards. This is what this line would equate to, and then we're just going to continuously do the checking, and we're going to do all these if statements, and then this line right here, line 17, is what points to this arrow. It's going to basically recursively call this function with the right children, or the right subtree of root. Okay. Yeah, and I think I think that might be it. Let's go ahead and try to run this, see if I made any mistakes. I think I made so I made a typo. This should be a capital. Wrong answer. Okay, so yeah, so I was searched into it a little bit, and like uh, the same tree problem, we have to store the values into variables. I guess you don't necessarily have to. You think you can do this in Python like an all-in-one line, but I like to store the values just to make it a little easier for myself. But what I did was I made some variables is left subtree, and I assigned it to what we had before, just this recursive call. So this is gonna come out to being either true or false, whether or not the subroot is in this left subtree. It's gonna come out to true or false, right? And then this variable is gonna come out to true or false as well, whether or not this subroot is in the right subtree of root, or if we pull up the whiteboard again, whether or not, let's go ahead and erase some of these, do it in yellow. Okay, so line 16 is going to return true or false, whether or not this value, or this root is, this tree subroot is the same as this subtree, right? Okay, and let's do it in a different color. Do it in this kind of reddish color. The next line, line 17, is going to return true or false whether or not this subroot is the same, this tree subroot is the same as this subtree, right? And then continuously, if we had more, nodes down here, then it would keep going. And our base cases are going to stop the recursion. So these are going to come out to true or false, and then basically if any of these, if left subtree is true or right subtree is true, whether or not we found our subroot in either of the subtrees of root, this is a little confusing, but I hope you're following, then we can return true. Otherwise, you just return false. And yeah, I think you can do this all on one line, but honestly, I'd rather do it this way, so it's a little more explicit. Okay, so I'm going to get into what I believe the time and space complexity is. These recursion problems are always kind of difficult to reduce the time and space, so correct me if I'm wrong, but I believe the time complexity, at least, time complexity, I believe that would be big O of, let's see, in the worst case scenario, we're going to have to go through every node in root, right? And then it's possible that we have to also, at every node in root, we're going to have to maybe check almost every node in subroot. So if the length or the number of nodes in root is, let's say, R, and the number of nodes in subroot is S, then I think the time complexity would be R, not plus S, but I think it's R times S. Because it's possible that at this node we'd have to check all the nodes, practically all the nodes, maybe 2 of them or 3 of them, to see whether or not it's a subtree, and then we'd have to do that at every single node, I believe. Okay, so after thinking about it for a little bit, I think the space complexity is O of R plus S, where R is the number of nodes in root and S is the number of nodes in subroot. I might be wrong on that. Yeah, so after some time thinking about the space complexity, honestly, I'm a little confused as to what it would come out to. So I'm just gonna not try to deduce that and not confuse you anymore. I think if any of you guys watching could explain it in the comments, that would be appreciated. Thank you.